Okay, today we're going to cover section 1.2. There's a lot of vocabulary and a lot of concepts. None of them are particularly difficult, but there are quite a few of them. So we're going to start with the concept of function. A function is a relation in which no first coordinates repeat. So if you have a set of ordered pairs, this is a function. Because if I look at the first coordinates, I have a 1, a 3, and a 5. That set of first coordinates, nothing repeats. None of those numbers repeat. This is referred to as the domain of the function. The domain is the set of all the first coordinates. Now, in terms of the definition, the range doesn't matter, but we'll go ahead and list the range. That's the set of second coordinates. So already, 3 vocabulary words. Function, it's a set of ordered pairs, or relation, that's a set of ordered pairs, in which no first coordinates repeat. The first coordinates are referred to as the domain, and the set of second coordinates is referred to as the range. All right, so let's look at another one. So this one is a function. This one is not a function. This one is not a function because the domain is 0 and 2, and that 0 is used twice. We don't write it twice. It's part of the domain, but it is used twice. So this one is not a function. And if you sketched this one, you would see clearly why it's not a function. We have the point 0, 1, the point 2, 3, and the point 0, 4. See these 2 points right here? They lie in the same vertical line. And what do you know about testing for functions? They have to pass what's called the vertical line. I'm having a hard time writing today. The vertical line test. And the vertical line test says that whatever your picture is, it's not a function if you draw a vertical line and it hits the curve in more than one place. So this is not a function. The vertical line test says if you draw a vertical line and it hits the curve in more than one place, it's not a function. So if I drew this, that is a function because no vertical line hits it in more than one place. Okay. Now, when we talk about, okay, so then let's look at some equations. So we talked about if we have a set of ordered pairs, if we're given a relation like this, we can tell if it's a function by simply checking to see if any of these guys repeat. If we have a picture, we can check to see if it's a function by doing the vertical line test. If you have an equation and you want to know, is this a function, you either have to visualize the curve or plot points and graph it. Now, this is an x squared, and we don't know a ton about x squareds, even though you did study them last year, but we do know that x squareds always have what shape? They're a parabola opening up. So this parabola looks like this. Oops. Is it a function? Absolutely, it's a function. It passes the vertical line test. If we had another equation, let's say we had a y squared equation. Now that I'm not as familiar with because I haven't spent as much time with that. It's got a squared in it, so I'm thinking parabola, but it's the y squared. So let's plot a few points. Let's set up a t-chart and plot a few points. Let's say x is 9. Then y could be 3, but y could also be -3. That's a problem. Why is that a problem? Because I have two, these are points, and I have two x's that are the same. This is not a function. If I graph this, it would look like this, and it doesn't pass the vertical line test. So somehow, when you're given an equation, you got to figure out if it's a function or not. Graph it. Does it pass the vertical line test? Set up some ordered pairs. Do any of the first coordinates repeat? Now, when we talk about functions, we are always very concerned with the domain of the function. Okay? So let's see, I don't want to erase everything here. So we're going to be concerned about the domain of the function. So let's suppose we have our y equals x squared function. Now, in function notation, that would be written f of x equals x squared. Remember, f of x is just the y value. Functions are input-output machines. So when we say find f of 1, what we really mean is let x be 1 and see what you get for y. Let x be 2, input 2, and see what you get for y. So the domain is the inputs, and the range is the outputs. Domain is the x part of the ordered pair, range is the y part of the ordered pair. Input, output. Okay, so if we look at this one, and I said, all right, what's the domain of this function? You would tell me that the domain of that function is all real numbers. The domain of this squared function is all real numbers, and that's the symbol for all real numbers. So I'll use that a lot. Now, when we're talking about domain, we're thinking about x, or we're thinking about the horizontal, okay? So as we go sideways on our number line, notice the curve just keeps going up, 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 out, 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 out. Forever and ever and ever. There's no breaks in it. Its domain is all real numbers. When you consider a function like this, that's a linear function. That's a line going through the origin with a slope of 2. What is its domain? All real numbers. X, forever and ever and ever and ever. Pick any x you want, you'll be able to plot a point. Pick any negative x you want, you'll be able to plot a point. It goes forever and ever and ever. The domain of most functions is all real numbers. There are really only 4 ways that you can mess that up. One way is in a word problem. A lot of times the word problem itself gives restrictions. So think about those projectile motion problems that we've been doing. If we were solving for t, and our ordered pairs in those problems were th, time, height, we did not want negative t values because they didn't make sense in the problem. Sometimes word problems and the practical application disallows some values of your variable. So you got to be careful with word problems. You also have to be careful anytime you have a variable in the denominator. An example of that would be f of x equals 3 over x minus 2. When you have a variable in the denominator, remember, you can't divide by 0. So x could not be 2. Your denominator cannot equal 0. So x minus 2 cannot equal 0, which means x cannot equal 2. Now, if this were a quiz question or something, that for the domain, this is my domain. I'm finding domain here. I'm figuring out what my domain is. Right now, I'm discussing potential issues with domain. Most of the time, it's all real numbers. But if you have a variable in the denominator, you must remember your denominator can't be 0. Therefore, for this particular problem, x can't be 2. So your domain is every number except 2. Now, if you write this, to me that means, okay, x can't be 2, but it could be everything else. The real mathematical way of writing it is negative infinity to negative 2, or negative 2 to positive infinity. That includes every number except negative 2, or excuse me, except 2, every number except 2. Now, I'm okay with you just writing this, but this is the real way of writing it. All right, so one thing that we have to worry about when we're finding domain is, do we have issues, or do we have a variable in the denominator? Another thing we have to worry about is a variable under a radical. So an example of that might be the square root of x minus 2. Now we know that whatever is under the radical must be positive, or I should say can't be negative. Must be something other than a negative number. Whatever is under the radical must be greater than or equal to 0. So in my example, x minus 2 has to be greater than or equal to 0. Whatever is under the radical must be greater than or equal to 0, which means x is greater than or equal to 2. Now, that is perfectly fine with me. If it says you must answer in interval notation, that would be 2 to infinity. Now, again, we're talking about what's the domain. What are the inputs that could go into this function? The only numbers you would be allowed to input into this function are numbers that are 2 or bigger. Because if you put in something less than 2, this is going to be negative and you're going to be imaginary. The third thing we have to worry about is if we have a logarithm of any kind in our problem, then we're going to have domain issues. We're going to talk more about that later. That isn't going to be a factor right now, but you do have to worry about inputs when you're taking the logarithm of them. And of course, the other one I said was in certain word problems, there are restrictions. So we already talked about that a little bit. So these are the big two that we are worried about right now at this moment. This one we've already been worried about, and that one we're going to get to at some point. So let me put another problem up here. All right, let's talk about what's the domain. Your job is to find the domain of this problem. Okay, so remember what you worry about. If you have a problem like this, kids, the domain is all real numbers. There is nothing to worry about. It's not a word problem, it doesn't have a logarithm, it doesn't have a radical, it doesn't have a denominator. Therefore, its domain would be all real numbers. This one, you have some worries. It has a radical and a denominator, okay? So radical, what do we know? Talking domain, what do we know about radicals? we know that whatever is under it has to be greater than or equal to 0. So x has to be greater than or equal to -1. So far, if I'm graphing this on a number line, I have this for my domain. But there's also a denominator. And what do I know about the denominator? The denominator cannot equal 0. So x minus 4 cannot equal 0, which means x can't equal 4. So we've got this restriction because of the radical. We have this restriction because of the fraction. So on my number line, that would mean that there's an opening at 4. I can't include 4. I have to skip over it. So my domain is everything from -1 to 4, or everything from 4 to infinity. Your possible input values are numbers here or numbers here. Those are the only numbers, if you were going to set up a t-chart and graph this function right here, set up a t-chart, these are the only numbers that you could put input into x. And then whatever came out would come out. Okay, let's look at number 21 in your textbook now, page 102. Page 102, number 21. Now, looking at vocabulary here, this has exactly to do with what we've been talking about. So do not be confused. Problem number 22, or 21, excuse me, 21, refers to the function g of x equals 3 over x. Now, your textbook says, tell whether or not it has a point of discontinuity at 0. Can you put 0 into this equation? No, you cannot. So the answer to the question is yes, there is a point of discontinuity at 0. Because you can't put 0 in. And if you have a number that doesn't work, that is not a graphable number. It breaks your curve. If the domain is all real numbers, you get a nice smooth curve where every point is connected and there's no breaks in it at all. It just goes. That means the domain's all real numbers. As soon as you say to me, x can't be 0, which is exactly right, x can't be 0, then I know somewhere on that graph, or I have some kind of a break. It's broken. It's in 2 pieces. Just like on the number line, there would be an open dot at 0 if you were going to graph the domain. You would tell me, well, you can't use 0, but you can use all of these or all of these. So you have 2 pieces, and it skips over 0. So then it says, so yes, we are discontinuous at 0. So then it says, okay, is it a removable or a non-removable discontinuity? Well, I'm going to tell you right now that it's non-removable. And that doesn't mean anything to you, but it will, because I'm going to do the next problem and show you the difference. So now the next problem is h of x is x cubed plus x over x. Now, looking at h, as it was presented, does it have a discontinuity at 0? The answer is yes. Kids, can you input 0 into this function? Can you say h of 0? No, you can't. Because when you put 0 into the problem as presented in the book, when you put 0 in, you get a 0 in the bottom, which is not allowed. Okay. So, upon closer looking at the problem, though, it looks like I could factor the top, take an x out of the top, and then cancel these guys and be left with x squared plus 1? Now wait a minute. Could I put 0 in now? Yes. So I removed the discontinuity. Now, how do you remove a discontinuity? You factor and cancel it out. You factor and cancel it out. So I could take out the discontinuity. There's a bug flying around here. I could take out the discontinuity. Now, if I needed to plug in 0 in this, I could. So that's called a removable discontinuity. This one was non-removable because there's no way to cancel that out. I'm stuck with it. Okay. Now, graphically speaking, removable discontinuities graph as wholes. If it's a removable discontinuity, it's going to graph as a whole. Now, what does that mean? That means that you get some nice smooth curve like this, but somewhere in it, there's an open dot. There's a hole in it. So when we say it is discontinuous, we mean it is broken. This is broken, but it's not broken too badly. We just kind of skip over that one little point. That's called a hole. That is a removable discontinuity. Removable. If it is a non-removable discontinuity, it's going to graph as a vertical asymptote. Now that is a complete break in the curve. Complete break. So you got a chunk over here and a chunk over here. That's not the picture of that one. I'm not saying that is. I'm saying that's what it looks like. This is what a vertical asymptote does. It completely splits the picture. They're not connected. You know, like these are still kind of connected. They're not connected. They're two completely separate pieces. So if your discontinuity is non-removable, it's going to completely break it into two pieces. If it's removable, it's just going to skip over that point. Okay, all right. Now let's look at number 25, because it has some more vocabulary in it that we have to know. So number 25 is some weird picture that has the point -1, 4, and 2, 2, and 5, 5. Now, I can't tell by the picture, and I'm not real excited by the picture, so I'm gonna go ahead and put arrows on the bottom. They did not, so it's a little bit unclear to me exactly what their intent was, but we're gonna look at this example with arrows on the bottom. And we're gonna talk about local maxes, local mins, identify intervals on which the function is increasing and decreasing. So we are going to talk about local, which are also called relative maximums, local or relative minimums. And when I learned all this back in the day, I learned them as relative maxes and mins. It's the same thing as local. I will use those words interchangeably. So I can't help myself. So just know relative max and min, local max and min, exactly the same thing. Then we have what are called absolute maximums, absolute minimums. And then we're going to talk about the intervals on which this thing is increasing and decreasing. Okay, now, if we look at the point -1, 4, that point is called a local minimum. Actually, local maximum. It's called a local maximum. Now, it's called a local maximum because when I draw the curve, I go up, up, up until I get to that point, and then I start back down again. That's the top of the hill. So in that space of the graph, It's the highest point. Now, it's not the highest point on the whole graph. That's the absolute max. The highest point on the whole graph is the absolute maximum. But in each little space that you look at, the highest point in that space is called the local maximum. The local for that space. Okay, so negative 1, 4 is a local maximum. Is there another local maximum? Absolutely there is. There's one at 5, 5. Why is there a local maximum at 5, 5? Because that's the top of another hill. When I look at this part of the graph, I go up, 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 up till I get there, and then I go down. That's the highest point. So think of the local maxes. You have a mountain range. The local maxes are the height of each mountain. Now, the absolute maximum is the highest mountain. So for this problem, the absolute maximum would be the 0.55. I hope that makes sense. Now, minimum. This is a local minimum. Why? Because the curve comes down, 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 down until it gets here, and then it starts going back up. So on this part of the graph, in that locality, the lowest point is 2, 2. It's a local minimum. Now, what about the absolute minimum? This curve does not have an absolute minimum. Why not? Because it goes down forever and ever and ever. So there isn't an absolute minimum. And when you tell somebody, oh, I've got a curve that has no absolute minimum, that tells them that it goes down forever and ever and ever. Okay. Now, let's talk about increasing and decreasing intervals. Well, it's exactly what you would think it would be. When we read a graph, we do it just like you write, just like you read English words. We read from right to left. So I'm going to put my pencil right here, and it's going to go up, 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 up until it gets to this point. So it is increasing on this interval. Now, when I'm talking about intervals of increasing or decreasing, I'm talking about moving from left to right. So I'm looking at x values. The x values from left to right. I know your pencil's going up because you're testing for increasing, but you are moving from left to right. So we're looking at x values. So I am increasing from negative infinity until I get to negative 1. Now notice, I'm never going to include the maximum or the minimum, because at that point, I am not increasing. I'm like steady. I've come up, I'm steady there, and then I'm going to go down. So these are open intervals. Now, am I increasing anywhere else? I'm increasing here. Aren't I increasing here also? So again, x values, I'm increasing from 2 to 5. I'm looking at the x values. Now, where am I decreasing? Well, I'm decreasing wherever my pencil's going down. So I'm decreasing from here to here. So that would be negative 1 to 2. And then I'm decreasing again from 5 to infinity. Those are my decreasing intervals. That's where my pencil is coming down. If I were looking at this picture, I would be increasing here, and decreasing just in this little space right here. If your pencil's going up, you're increasing. If your pencil's going down, you're decreasing. Okay, now we've got another vocabulary word to talk about. We're going to talk about boundedness. Boundedness, pretty simple concept. If a function has a ceiling, it's bounded above. So when you graph it, if there's a point that you don't go past, it's bounded above. if there's a floor, it's bounded below. And if it is bounded above and below, so it has a floor and a ceiling, then it is considered bounded. So when someone says to you, is this function bounded, it must have a ceiling and a floor. If it only has a ceiling, it's bounded above. If it only has a floor, it's bounded below. So let's look at the function we were just looking at. Does it have a highest point? Does it have a ceiling? The answer is yes. This guy is bounded above. By what? What is its ceiling? Where is its ceiling? Its ceiling is up here, which is at 5. It's bounded above at y equals 5. Now, is this one bounded below? Does it have a floor? No. So therefore, it is not bounded. It is only bounded above. All right, let's look at another one. Another picture that we might have. So we have a picture like that. This is a horizontal asymptote, the curve's approaching it but never intersecting it. We want to know about its boundedness. Okay, does this one have a ceiling? Is it bounded above? Absolutely not. It's shooting up into space. Is it bounded below? Does it have a floor? Does it bottom out somewhere? Yes, it does. This one is bounded below by y equals -2. Let's look at that one. Is that bounded above? Does it have a ceiling? Yes, it does. It's bounded above at y equals 4. Does it have a floor? Yes, it does. It's bounded below at y equals 0. Therefore, it is said to be bounded. Remember, but there's 3 things. There's bounded above, bounded below, and bounded. And the only way you can be bounded is if you both have, or if you have both a top and a bottom. Now, some curves have no boundedness at all. That guy is, there's no boundedness at all. It's not bounded above, it's not bounded below. And then we've got an example of each of the other kinds there. Okay, now, there will be some problems in this section where you are asked to find the maximum. So let's say they give you an equation, so they give you a function, you know, f of x equals, and say, use your calculator to find the maximum or the minimum or both, all right? So you sketch it on your calculator. Okay, whatever it looks like. You sketch it on your calculator. This would be the maximum point. That's what they mean by the maximum. Now, that is not the absolute maximum. I get that. There is no absolute maximum. But your calculator will, but the problem will say find the maximum, and what they mean is find the relative maximum. Okay, so it's right there. Now, before, when we were graphing, every time we graphed, we were looking for these points. So we didn't really care if we could see the top or the bottom. It really wasn't relevant to us because we were looking for the zeros. We were solving the equation, setting it equal to 0 and finding out what gave us that 0 value. Now, we're not doing that. Now we are actually interested in the high point and or the low point, which means you have to see it on your graph. If you don't see it on your graph, change your window so that you do. So if you have your window set from -10 to 10, and the peak is somewhere else, make that -10 to 20, or -10 to 30, however big it has to be, so that you can see that point. And likewise, on the other end, the low point. Now, I'm not going to go through this with you because it's exactly the same way that we found these points. Get it graphed, make sure you can see the points you're looking for, go to second calc, and before we chose the 0 option, now we're going to choose either the max option or the min option. And then as soon as you press that button, it will say left bound. So set your left bound over here somewhere to the left of the maximum, right bound over here to the right of the maximum. Set it up here, take a guess, hit enter, and it will give you the coordinates in the actual ordered pair for that point. And likewise for the minimum. Second calc, min, or minimum, I can't remember if it has the whole word written out, and then left bound over here, right bound over here, take a guess, hit enter, and it will give you the minimum point. So that's easy, and by the way, we'll be doing a lot of that later in the year. Again, I don't anticipate you're going to have a bit of problem with that because we've already discussed it about a zillion times. I think you'll do great with that. Now, we got some more vocabulary that we got to get straight. We need to talk about symmetry. Okay? Now, there are basically 4 symmetries that we're going to be concerned with. One of those is symmetry about the y-axis. Now I'm going to draw a picture here. I'm not a very good artist, but I have a parabola, vertex at the origin opening up. That is said to be symmetric about the y-axis because if you could crease your paper on the y-axis, crease it, fold it together, these would come together. These 2 pieces would come together. In other words, this side of the curve is a mirror image of this side. That is said to be symmetric across the y-axis. Now, in terms of vocabulary, if a curve is symmetric about the y-axis, it is called an even function. An even function. There are lots of even functions. This is our friend cosine. This is the cosine curve. Now, you don't know that now maybe, but trust me, in a couple days you will. This is the cosine function. Is the cosine function even? Yes, it is, because what's on the right is a mirror image of what's on the left. Look, fold it over, fold the 2 pieces together. They will be right on top of each other. It is symmetric about the y-axis, even. We also have symmetry about the x-axis. And a simple example of that would be something that looked like this. Does that have symmetry about the x-axis? In other words, if I folded my paper on the x-axis, would the 2 pieces come together? Is this a mirror image of this? Yes. That's symmetry. That's symmetry about the x-axis. Now, you will notice I've got symmetry about the x-axis, but I do not have a function because that's not going to pass the vertical line test. Because it's not a function, and so it won't pass the vertical line test, this does not have a special name. Like y-axis symmetry is even, it's all good. X-axis symmetry, not so good. So, I mean, it's okay. Some things have it, and it's good to know that, and it can help me sketch, but it doesn't have a special name. There's no name for that. We also have symmetry about the origin. So a beautiful example of that would be this curve. Here's the origin. Now it's a little bit harder to envision this because we don't really have a line to actually crease the paper. But if you flipped your curve, reflected your curve across the origin from quadrant 1 to quadrant 3 or from 2 to 4, that would be a mirror image, right? That is symmetric about that point, about the origin. A function that is symmetric about the origin is called odd. And you'll remember that because origin and odd both start with O. So if somebody says to you, is a function symmetric about the origin, you will have to determine, or excuse me, if they say, is it odd, you'll have to determine if it has symmetry about the origin, and I'm about ready to show you how to do that. But we have one more to talk about. We also have symmetry about the line y equals x. Now, the line y equals x is the identity line, so I'm going to put it in there nice and dotted. If I put a curve here and a curve here, and I folded my paper on the line y equals x, which is the identity line, if I folded my paper, would that piece come over and land right on top of this piece? Yes. To be symmetric across the identity means that if you fold your paper on the diagonal, the curve will double back onto itself. Now, I want to point something out. This curve is symmetric about the origin, but it is also symmetric about the identity line. If I fold my paper on that dashed line, this is going to double over on itself. So it is possible for curves to have more than one of these symmetries. This one is symmetric to both the origin and the identity line. Okay, all right. So we know now, we understand what it looks like to be symmetric about the y-axis, the x-axis, the origin, and the identity. Now, I'm going to give you an equation and ask you to tell me what kind of symmetry it has. So here's an equation. And you're going to tell me whether it has symmetry about the x-axis, the y-axis, the origin, or the identity line. Okay? The question is, what symmetry, if any, because it is possible for a curve to have no symmetry. So is there symmetry to any of these, or about any of those things? Okay, so for x-axis symmetry, to check for symmetry about the x-axis, shoot, I wish I hadn't changed my thing. For symmetry about the x-axis, notice that if this is the point 3, 4, this would have to be the point 3, -4. So in other words, the sign on y, changing the sign on y doesn't impact the x value at all. So you should be allowed to change the sign on y without causing any problems. So to test for x-axis symmetry, simply change the sign on y and see what happens. So in this equation, you're looking at the same as further, there's not even a y. Remember, f of x is the same as y. So there's my equation, okay? Now, -y, change the sign on your y. So -y equals x cubed minus x. or simplifying, y equals negative x cubed plus x. Now, did changing the sign on that y change the equation? Well, heck yeah, it did. If you have symmetry, it won't change it. If you have symmetry, this will turn out exactly the same as this. Well, it didn't, so we do not have x-axis symmetry. If you're going to have symmetry, it means you can change the sign on y and not change the equation. Well, we did, so it's not. Now, y-axis symmetry, think about it. On the y-axis, point over here, point over here. I can change the sign on x without impacting the equation. So for y-axis symmetry, I'm going to change the sign on x. So in my equation, y equals negative x cubed minus negative x. So y equals, simplifying, negative x cubed plus x. Does that match the original? No. So I don't, when I graph that, it's not going to have symmetry about the y-axis either. Well, what about the origin? Well, think about it. If you have symmetry about the origin, you go from positive, positive to negative, negative. So we're going to change the sign on both. So for our equation, we'll have negative y equals negative x cubed minus negative x. So negative y equals negative x cubed plus x. Y equals x cubed minus x. Wait a minute. That matches the original. So I could change the sign on both and match the original. So therefore, we have symmetry about the origin, which, oh, by the way, if we're interested, means we are odd. This is an odd function. To test for symmetry about the identity, you switch x and y. So your equation would be x equals y cubed minus y. Is that the same as the original? No. Therefore, we are not, or we don't have symmetry to the identity line. Now, a lot of times kids will say, well, Mrs. Ford, are there any functions that you can switch the x and the y and end up with the same thing? Because that seems a little bit hard to imagine. So let's go back to that function that we looked at earlier that had the non-removable discontinuity, x0. If we're this is the original. If we're testing for symmetry about the identity line, we switch the variables. Now that does look different, there's no question about it, but let's do some rearranging. Let's multiply over to here, and let's divide by x. Uh-oh, that was the original, and this is what happened when I switched x and y, and they're exactly the same. So this one would have symmetry about the identity line. This is an example of a curve that has symmetry about the identity. Now, is it possible to get no all the way down? Absolutely. Most things don't have these symmetries. Is it possible to get more than one? Yes. Yeah, we saw an example of that earlier. So you just don't know. You just have to go through and do each individual test and see what happens. Okay? All right. So now we've done that. We have one more thing to talk about, and that is asymptotes. We have already discussed asymptotes in terms of vertical asymptotes. So who remembers, who's taking good notes, who's paying any attention, what's going on here? Where do vertical asymptotes come from? Vertical asymptotes, they came out of this problem right here. This is when we talked about it. Vertical asymptotes are when the denominator equals 0 and you can't get rid of it. Remember, if you can get rid of the discontinuity, it's not going to be an asymptote, it's going to be a hole. Vertical asymptotes are when the denominator equals 0. Denominator equals 0. That's what the vertical asymptote is. I was going to write out the word 0 for some reason. Denominator equals 0. That's how you get vertical asymptotes. So if someone says to you, let me put a couple functions up here. Somebody says to you, let's say f of x equals 3 over x plus 1. F of x equals x minus 4 over x plus 2, or 1, I guess. F of x equals 3x squared plus 5 over x minus 3. And f of x equals x plus 1, x minus 5 over x plus 1, 2x minus 7. We'll do one more. F of x equals x plus 1, x minus 2, x plus 3, x minus 4. Okay, let's look at these 5 examples. And we're going to go through and find horizontal asymptotes and vertical asymptotes for all of them. We're going to do the verticals first. So the vertical asymptote for this problem, where is the denominator 0? The denominator 0 at x equals -1. So your vertical asymptote is at -1. Vertical asymptotes are cannot be's. Absolutely cannot be, ever, ever, ever. And that would be -1 in this case. What about this one? Where's the vertical asymptote in this one? X equals -1. I don't care. My eyeballs are not looking at the numerator. My eyeballs are focused on the denominator, because where do vertical asymptotes come from? The denominator equals 0. Okay, now I look at this one. Where's the vertical asymptote? The denominator equals 0 at 3, if you're putting 3. So x equals 3 is my vertical asymptote. Now here I put a tricky one in. What do you notice about this problem? We got an issue at -1 and at 7/2. But what about this one? It cancels. That is not a vertical asymptote. That would have a hole at x equals -1. It has a vertical asymptote at x equals 7/2. Because if you put 7/2 in, you get a 0 in the denominator and you can't get rid of it. You can't cancel it out. It's like all of these. It's just there. So you got a vertical asymptote at 7/2. Okay, now we look at this one. Well, wait a minute, nothing cancels. So I have 2 vertical asymptotes. X equals -3 and x equals 4. There are 2 numbers that make the denominator 0. Neither one cancels out. So I have 2 vertical asymptotes. So if I were graphing that one, which we're going to learn how to do, by the way, hold your breath, we'd have a vertical asymptote at -3 and a vertical asymptote at 4. So that picture would be completely broken twice. So there are going to be 3 chunks to that picture. Completely broken twice. So that's vertical asymptotes. Now horizontal asymptotes are a little bit more intuitive. They're not quite as cut and dried, I mean. Okay? So let's talk about that for a minute. And I'm going to talk about it with this problem first. Okay, I'm going to do these 3 problems first, because they're kind of normal. Those are weird. You'll see what I mean in a minute. Horizontal asymptotes are what we call limits. They're what happens to the problem, in this case the fraction. What happens to this fraction as x gets really, really big? And I don't mean really big like 100. I mean really big like a billion. What happens when x gets really, really big? Well, if we let x be a billion, on the top you'd have a billion minus 4, and on the bottom you'd have a billion plus 1. Now wait, isn't a billion plus 4 just about a billion? And isn't a billion minus 1 just about a billion? I mean, really, if we're talking about billions, these don't really even count. We basically have a billion over a billion, which reduces to 1. X over x, 1. These don't really count if you're talking about billions. They're really not important. Similarly, look at this one. Now these are gone. I've canceled those out. They are gone. I am now looking at this part of the problem. Now think about a billion again. Think about putting x equals a billion. On the top, you'd have about 1 billion. Putting a billion right here. This would be about 1 billion. And on the bottom, you'd have about 2 billion. I'm not saying exactly, okay? We're talking about limits here. We're not talking about exact values. The top would be about a billion, and the bottom would be about 2 billion, which when I make the fraction gives me a value of 1 billion over 2 billion, which is about 1/2. X over 2x. That's my limit. That's my asymptote, my horizontal asymptote. This one. If you FOILed, the highest power you'd have on the top is x squared, and then some other stuff. I'm not even interested in the other stuff. Okay? Remember how I wasn't interested in the 5 and the 7? Because they paled in comparison to a billion? Well, everything, when you talk about huge numbers like a billion, and you start squaring them, everything else pales. So I don't even care about this other stuff. I know on top I'm going to have an x squared. And what am I going to have on the bottom? An x squared. Again, couldn't care less about all the other stuff. I'm focusing in on the biggest power in the problem. Here it was x to the first. Here it was x to the first. Here it is x squared. So I am zeroing in on x squared. I don't care about the rest of this junk. So what do I have? X squared over x squared. My horizontal asymptote is y equals 1. X squared over x squared. Now what makes this problem different is, look at the other three we've done. We had x over x, we had x over 2x, and we had x squared over x squared. In all those problems, I had the same power of x on the top and the bottom, so I could just compare them. It's like having 5x plus 3 over 2x minus 7. I just compare them. So the horizontal asymptote would be y equals 5/2. If I had 4x squared minus 2x plus 3 over 7x squared plus 9x plus 1, the horizontal asymptote would be y equals 4/7. Whatever the highest power is, you're looking at that fraction. Now what's the issue here? The highest power in the problem is x to the first, x, but I don't have 1 on the top. So I'm going to say 0x plus 3. I have no x's on the top, and I'm going to put a 0 in there. Now I can compare my x's, and I have 0 over 1, which is 0. 0x over 1x, 0. here, I have the same problem, but kind of in reverse. The highest power is x squared, but I don't have any on the bottom. That means my horizontal asymptote is at 3 over 0, which is undefined, so this has none. In other words, there's no limiting thing. There's no limit to this. It's going to shoot up into space, shoot off into space forever and ever with nothing to limit it. No horizontal asymptote kind of containing it or holding it in. So the moral of the story is, got a lot of stuff scratched up here. The moral of the story is, if the powers on the top and the bottom match, that's your horizontal asymptote. If the power on the bottom is bigger, this one, remember, didn't have an X down there. If the power on the bottom is bigger, your asymptote's going to be at 0. Your horizontal asymptote's going to be at 0 every time. If the power on the top is bigger, remember, this didn't have that. If the power on the top is bigger, there will not be a horizontal asymptote. There will be another kind of asymptote that we'll discuss at some point, but it won't be horizontal. Okay, one more question to look at. I want to look at question number 84. A continuous function, now I'm on page 105, problem 84. A continuous function has domain all real numbers. Okay, so I have a continuous function. It's not broken, not discontinuous, removable or non-removable. It is not broken in any way. I have a continuous function. Domain is all real numbers, and f of -1 is 5. That means if I input -1, 5, or if I input -1, I output 5. So that's the point, -1, 5. And f of 1 is -5. So if I input 1, this is f of x, if I input 1, I output -5. Okay? Now, explain why f must have at least one 0 in the interval -1 to 1. Now, what does it mean to be a 0? It means it's an x-intercept. So explain to me why there has to be at least one x-intercept in between these two dots. Remember, it's a continuous function. That means all the dots are connected. There aren't any breaks. Everything is connected. So I have no idea what this thing looks like. I'm going to just sketch something in here. No idea what it looks like. But how do I absolutely know there has to be a 0 between these 2 points? Because those 2 points have to be connected. And if one of them is on top of the x-axis and the other one's underneath the x-axis, when I connect them, won't I have to cross the x-axis? Yes. So that's the explanation. It's a continuous function with no breaks. That means every dot is connected. And when I connect these two, which are the two they gave me, I will have to cross the x-axis. I have no idea what the picture looks like. I randomly made that up. But I do know that in between here and here, it crosses the x-axis. It has to if those 2 points are going to be connected. And they are connected. All right, that's that. You should now be able to do all the problems in section 1.2. Have a great day.